Okay, let's get started. Here we go. So this is where we left off last time. Let's finish up this example. So what do we have? We had this trough. It's like a long trench. It had a cross section that was trapezoidal, and it was half full by height, right? So it was half full by height, and we wanted to figure out how much work it took to empty this trough. So what does that mean? That means getting all the water out the top of the trough, basically out to this. Once we get the water to this level right here, then we consider it just spills over the side. So we got to get all the water to that, up to that. And so one instinct that lots of students have that kind of is indicative that you're really not understanding the whole point of this is that students will find all the volume of the water because they know that volume times density gives weight or mass. You could turn it into weight. Okay? So why don't we find all the volume of the water? Thousands of calculus students throughout the ages have done this to try to solve a problem like this, finding all the volume of the water in one lump chunk. Okay, is that what you're going to say?
I was going to say because it's constantly changing as you remove water.
What's constantly changing? What's it?
The amount of water in the trough.
Okay.
As you take water out, there's less in there.
Okay. But that doesn't really get at, so you were talking about...
It takes less energy to move, if you were to take a thin layer of water on top, it takes less energy to move that all the way up.
Okay, right, so all this water in here, depending on the depth, has to go a different distance, and work is force times distance. Okay, this is a huge point, because we see this every semester. I see, you get a problem like this, and students find the volume of all the water. And right away, when we grade that, it just says to us, you don't get it. You don't understand the point. And this is kind of the point of all of integration, is that as soon as you go a little bit deeper, you've got a different distance to move that water. So finding the volume of all the water is just not going to help. It's not going to help. So what do we do instead? So in red, I drew this layer, right? This layer of water, all at the same depth. So we want to use force times distance. We want to find some kind of element of water for which we can calculate force times distance. And so that will mean water that all has to go the same distance. So what is that? A horizontal layer. A horizontal layer, right? A horizontal layer all has to go the same distance. And so for that horizontal layer, we can actually do F times D. So that's what we're going to do, right? So it's about finding a little bit of work. And so I should have drawn this out. So this is going to look like this. This layer... then it's going to look like this. Do you see that one layer of water will look like that? And all that water in that layer, because it's thin, will virtually have to go the same distance. Okay, so we want to calculate the work for that layer, which is force times distance. What's force? Force is weight, right? So when we're lifting something, the force to lift something is its weight. So this is weight. Okay, and then we have a frame of reference. So we named our frame of reference, x was the distance from the top. And that's where we're trying to get the water to. So x is the distance from the top. So what distance does that layer have to go? X, right? That's what we had, right? X. And then so now we got to get the weight of that layer. Okay, and so that weight is going to be we're in metric. If we were in English, we could go right to we'd have weight density right away. But to get weight density, we're going to have to do m times g, and then times what? So this will be weight density. So it's over here now. So the mass density of water times G gives the weight density in newtons per meters cubed, and we need newtons. So we need to multiply by the volume of that layer, and the volume is just going to be width times length times height. So that's what we got. So the length was 2 meters. The height was our delta x, a little change in x. And then the width of these layers changes, right, with depth. So this is where we're going to have our linear relationship. So here's where a function, we're going to have to make a function, right? This is where a function serves us well, because depending on x, we get a different width. That's exactly what a function is about, right? That's what a function is about. So now we want to come up with that. So what is that linear relationship? So weight density times volume gives weight, and that's the force to lift it, times x. So that's all over here already, but I just want to finish that thought. But okay, so now coming back over here, so now where I've got room, we need this relationship. Given an x, what is the width? So we get this, we know we have a changing width, and we need it in terms of x. So this is where it's going to be linear because the sides are straight like this. So we can set up x and w. Right? We can make some ordered pairs. So what do we know? When x is 0. Yeah, we could use that. So just pretending that it's all the way filled up, we could do that. When x is 0, the width is? No, when x is 0. So I think this is not an 8. Sorry, it's a 0. So when x is 0, and it's about the relationship of the sides. It's not about where the water is, right? So we're just trying to get the relationship of the sides. When x is 0, width is 1 meter, right? 1 meter. What else do we know? When x is 0.5, width is 0.6. Okay, we could also, if you wanted, you could have an ordered pair in the middle. You know it's linear, so that when the x is halfway between these two x's, the width will be halfway between these two widths. So you could do 0.25 and 0.8, but we don't need it. All we need is 2 points for a line, right? So then we have rate of change of w with respect to x would be, so 0.6, it's actually negative, right? Negative 0.4 over 0.5, negative 0.6 minus 1, or 0.5 minus 0, so negative 4/5. And then we have a y-intercept. I think every example we've had, we actually had the y-intercept. What if we didn't? So what if we didn't have the y-intercept? We'd have to still come up with the equation of this line. So suppose we're going to use this point instead. So we can do that. The final width is initial width. We can do 0.5 plus. How much the width changes? Well, it changes at a rate of negative 4/5. And for any x, the change in x would be x minus 0. This is 0.6. So if you had me for Calc 1, you should remember this. A final width is initial width plus the change in width. And how do we find the change in width? By the change in x times the rate of change. Right? So this is the change in x times the rate of change gives the change in width. Add it to the initial width, and you get any width at any x. Right? And that would be the same thing that we should get. That should give us a y-intercept of 1, does it? 4/5, yeah, because negative 4/5 times negative 0.5 is 0.4 plus 0.6 is 1. Okay, so we got this relationship, and so now we're ready to set up the volume of typical slice. So this, the volume of a typical slice is, we got our 9800 what is that? Weight density times volume. Volume's going to be 2 times, I'm going to change this to -4/5 x plus 1. That's what that is when you simplify it. Length times width times height, delta x. So that thing in brackets is the volume of the slice times the weight density gives the weight or the force, and then times the distance we have to move it, which is x. So there's our typical amount. That's the work for a typical slice. That's the work for a typical slice. It's a function of two things, right? It's a function of how deep the slice is and a function of how wide the slice is. Which is a function of how deep it is, right? Which level we're at. So the width is a function of x, and the work is also a function of x there. Questions on that? So this is the hardest part of these problems. There's really only one more thing to think about, and that's the bounds of integration. But let's make sure this is really probably the hardest part. Any questions? Yes, sir?
Yeah, what's the difference between the height?
I'm talking about the height of the height of the layer is h. It's delta x, and now we have to move that layer a distance of x to get it out. Yeah, so x is the distance we have to move the layer. When I say height, I'm talking about just that little tiny height of the layer. Other questions? Yeah. Oh, this is all times. Everything's times. This is the weight density times the volume. Right there? Is that what you're confused about? Still looks like minus. How about that? Yeah, weight density times volume is weight. Yeah. Other questions? Yeah. Say it, what was the last thing? I got it all except the end. So this is the force. This is the weight. This whole thing is the weight of the slice, or this whole thing right here. But work is force times distance. So it's the weight or the force of that thing times the distance we have to move it. How far do I have to move the tip of that slice? How far do I have to move that slice? 50 minus x? Well, but my frame of reference is this way. See, my frame of reference is from the top. So yes, if my frame of reference was this way, then yes, it would be 0.5 minus x. But I set my frame of reference, and so this is where the bounds would come in. So you could do that, and then you would have different bounds of integration than I would, and then we get the same answer. Yep. Okay, so total work then is going to be, we're going to sum up all. I won't write this again. All that dx. Oh, sorry. Well, okay, hold on a sec. So the delta x becomes this dx, all right? So I'm going to rewrite it. 9,800 times the 2 times the -4/5 sec, the width, this is the width at any depth x. And then the dx, I'll pull the dx that way out to the right, and then times x. So just rearrange things, and things got really small, right? Okay, so the question is, what layers are we removing? What layers are we removing? So the first, and they're x's, right? They're x values. So what's the first x value that represents a layer we're removing? No, yeah, so the water is only half full in this thing by height. So if the whole thing were full, then we'd start with x equals 0, but it's not. So here's the top layer, and that's at x equals 0.25. The first layer is at 0.25, and then I want to sum up the work for all the layers all the way till x equals 0.5. So this represent, those bounds of integration represent the first and last layers of water that I want in terms of x, right? The first layer I want is the 0.25 at the top, and then the last one I'm going to take out is the layer at 0.5. Okay, anybody have a question about that? Yes, please.
Why is the initial width 0.6 if the initial x is on top?
Oh. Oh, no, yeah, that's right. Yeah, so I'm using this point. Are you talking about building this equation of this line? Yeah, so I'm using this point. So we can use any point, any ordered pair, and call it the initial point in terms of building that line. Does that make sense? So I could choose any, I could choose 0, 1 to be my quote unquote initial point, but I chose this one pretending that we didn't have the y-intercept to show you a different way. So then in terms of building this line, I'm calling that the initial point. Does that answer it? Okay. And so then, yeah, we got y initial plus change in, or w initial plus change in w, where 0.5 is x initial. Okay, all good questions. Any other questions? All right, and then, on a quiz, test, homework, you may be asked just to set it up and quit, or you may be asked to solve this. The solving it should just maybe will take a little time, but should be the easy part, okay? In terms of just this is multiply everything together and you got easy polynomial. Okay, so but in terms of a question that you might be asked, anything's fair game. Set it up, because that's what I'm most interested in when it comes to something like this. But you could be asked to actually find the work, and then you do the antiderivative and use the fundamental theorem. Another example, last chance. Okay, here we go. So let's do a half. Get distraction away. Okay, so let's do. Got a giant spherical bowl like this. But there's a pipe. Oops. Okay, so this thing is filled up with, what should be filled up with? Sand. Sand out of pipe. Probably not. All right, so anyway, I'm going to fill this thing up. And say it's something that has a density of, let's say it's something with a density of 1250. Something denser than water, okay? Something denser than water is 1,000 kilograms per meter cubed. So something denser than that is in there. It's all filled up, and we've got it. We want the work to get it out this pipe. And this pipe is 1.5 meters. And we'll say the diameter of the tank is 6 meters. So we got a big spherical tank, and then there's a 1.5 meter pipe. And so what's the work to get the water out the pipe, right? So what's the work to get the water out the pipe, or the liquid? All right, so why don't you take 5 minutes to talk and see what kind of progress you can make on this. And then we'll regroup. Yeah, question? It's a spherical half sphere. This is a half sphere tank, like a bowl. Okay, and so we're on the same page. We're gonna call up and down dimensions in this problem y. And we're gonna call left and right dimensions x. So that's just so we're kind of on the same page here. There's still different ways to do it, but whatever you're calling an up and down dimension, use y. Whatever you're calling a side by side dimension, use x. This way. So that's a little different than what we've done. You still have some choice in that, but you do that. We're gonna solve this and take advantage of this example to talk about different frames of reference. Okay, because there's many ways you could choose your frame of reference, but there's two kind of obvious choices, right? The first is that y is going to be the distance down from the top of the bowl. So that's this one over here, like this. So let's do that one first, okay? The other one is going to be that y is the distance down from the top of the pipe where the water's coming out. Both will work. Both will get the same answer. And if you can set up both, then it's proving a greater level of understanding, okay? But the frame of reference is a huge thing with these problems. So by looking at two different versions or two different frames of reference, it can really help us understand, okay? So this first one, y is the distance down from the top, okay? And so we're going to find a little bit of work on what? So, right, so again, if you just find the volume of half of a sphere and say that's how much liquid we have, you're missing the point. You don't get it, okay? So how are we going to do this? We need to find the work for what? Right, a typical horizontal slice of water that all has to move the same distance. And what will that be in this case? If you take a slice in this, what do you get? You get a pancake, right? Okay, so we're going to have our little bit of work for a pancake. All right, and so that will be force times distance. What's the force? It's the weight of the pancake, right? And so the weight is going to be the weight density, which is 1250 times 9.8, right? I gave you mass density. You need weight density. So in metric, if you're given mass or mass density, you need to change it to weight or weight density, all right? And so that's the weight density, and so to get the weight or the force, it's going to be times the volume of the pancake, right? Times the volume of the pancake. So that'll be our F. And then, for this frame of reference, what is the distance that it has to go? So, yeah, so we have y down like this. But that's not the distance it has to go, right? It has to go what? No, y is down from here. Yeah, so it's going to go a distance of y plus another 1.5 feet. In this frame of reference, that's how far a layer has to go. It has to go to the top, where y equals 0, and then another 1.5 feet. Does it make sense? Okay, so what's left to do? We got to find the volume of a pancake. So we got our 1250 times 9.8. Volume of a pancake is the same as it's always been. Pi r squared times the height. The height is little change in y. So weight density times volume gives weight. And the weight to lift something is the force to lift something is weight, right? Times y plus 1 plus y. So what's left is the radius. Radius is constant or changing? Changing. It's changing according to y. So we're going to take ordered pair at the top, ordered pair at the bottom, and find the equation of a line, right? This is different, right? It's not a linear relationship between y and radius. Instead, it's according to a circle, right? So this, we're not going to find a linear relationship now. We're going to find a circular relationship. So if we truly put our center of our frame of reference there, so this is y, and this is x, then what is the radius in terms of x? You see that the radius is just then x, right? It's just the x coordinate of the point on the circle. From here to here is just your x coordinate of the point on this circle. Radius equals x. So I want to choose the center, the origin of my frame of reference as conveniently as possible. If I choose it right in the center of the sphere, then that circle, any disk has a radius of x. You see that? So now what is the relationship between y and x? What we need to get, so this is going to be x squared then, but we need to get it in terms of y, right? So this radius squared is the same as x squared. But we need to get it in terms of y. So how do we do that? So we need the equation of that circle, which is, yeah, x squared plus y squared equals 9. The radius is 3, so it's going to be x squared plus y squared equals 9. R squared. And it's just x squared plus y squared, no subtractions in there, because I put my origin right in the center of the sphere, right? So it's like x minus 0 squared plus y minus 0 squared equals r squared. So therefore x is square root of 9 minus y squared. And the radius of our pancake is the same as the x-coordinate because I put the origin there. So here we go. We got the 1250 times 9.8. That's what? Weight density. Hi, so we need r squared, which is x squared. So really, yeah, so we could solve for x and plug it in here, or we just say, we could solve for x squared. What is x squared? Yeah, we could just solve for x squared. That's what we need. We need x squared, so we just say 9 minus y squared. Delta y. times y plus 1.5. So, weight density, volume of the typical pancake, it's a function of depth, right? Times the distance that pancake has to move. So all that's left now is limits of integration. In this frame of reference, we're going to look at what are the y values for the, say, the highest layer in terms of y, all the way down to the lowest layer that we have to move. So y starts at? No. So let's look at the top layer. What's the y value at the top layer? 0. And then what's the y value at the bottom layer? 3. 0 to 3. And this time what we're at, just know that that delta y, when things get small, is our dy, right? So that's frame of reference 1. Let me pause for questions. Any questions on that? Why we did everything that we did there? Okay, in frame of reference number 2. What's going to be, so will the weight density be different?
No.
Will the volume of a typical pancake be different? Well, kind of. So now that y is up here, so y, now we have this. That's y. And then at our x-axis is at the level of the pipe, x. So what happens here? When we come to the point where we're finding this radius, we have a different equation of our circle. Do you see that? So now what's our equation of our circle? What's the center of the sphere? Center of that sphere is at? No, the center of the sphere. No, the center of the sphere is at a point, a ordered pair, 0, comma. Try again. The center of the sphere is at 0. Nope, not 3. 1.5. The distance from our x-axis, where our pipe is, down to the center of that sphere is 1.5. So the center is now 0.5. So 0, comma 1.5. So that circle is what? X squared plus y minus 1.5 squared equals still 9. So the radius is still 3. So that's the equation. When we put our frame of reference up there at the top of the pipe, the center of our circle is no longer at y equals 0, it's at y equals 1.5. So we have this new circular equation. All right, so here we go. So now the volume of the work for the pancake is going to be 1250 times 9.8. Times volume of the pancake, pi. So is the radius still x? Is the radius still x? So from here to the radius of our pancake, is it still x? Yes, so we need radius squared. And what's it in this case now? Is 9 minus y minus 1.5 squared. Times delta y. So again, this is volume of the pancake with our new frame of reference. Okay? And now, is the distance y plus 1.5 now? The distance that the layer has to move? What's the distance the layer has to move in this frame of reference? Just y now, right? So if the layer's down here, it's got to get up to here, which is exactly what y is. So rather than having y plus 1.5 now, it's just times y. And then what about our limits of integration? So what's the y value of the first layer that we have to move? It's no longer 0, but 1.5. And the layer of the last, or the y value of the last layer we have to move is? 1.5 plus a radius, 3. That's right, so 4.5. So what happened? The equation of the circle changed, the distance the layer had to move changed, and our limits of integration changed. All by 1.5, right? If I move that frame of reference by 1.5, then everything, what, changed by 1.5? This changed by 1.5, that y value changed by 1.5. That distance it moved had to change by 1.5, and then our two limits changed by 1.5. So it's like we just shifted the whole thing by shifting the frame of reference. It shifts everything in the formula that we set up. Both will give the exact same answer. Okay, ask if I lost you, because you're probably not the only one who has the question that you have. All right, so there's a trade-off, right? So in this case, this got hard, the equation of the circle got harder, but then the distance that it had to move got easier, right? So it's like sometimes there's a trade-off. So maybe in the end we prefer the first way. Who knows? Okay, but it's just there's kind of always a trade-off with choosing your frame of reference. It's going to make maybe you choose it to make one thing very convenient, but then something else might not be as convenient. Last chance for questions. Okay, so we've done enough examples of work emptying that you're good to, hopefully you've got everything you need to finish the web work for that. So the next topic is hydrostatic pressure. Hydrostatic pressure. We're going to introduce that. Or force, hydrostatic force, okay? So given some region R, the total force on that region would be the sum of lots of little bits of force. Should sound like a broken record, right? If you want to find total area, you sum up. What do you sum up? If you want to find total area, you sum up little bits of area. If you want to find total volume, you sum up little bits of volume. If you want to find total work, you sum up little bits of work. So if you want to find total hydrostatic force, you're going to sum up little bits of hydrostatic force. What do we mean by that? So this is like the force of some fluid on a surface that's submerged in that fluid. Okay? So why do we need this? Why do we need integral? Why? Because the pressure on something submerged the pressure will change with depth. Okay? And so pressure is weight density, same kind of weight density we talked about before, of the fluid that you're using. That's either newtons per meters cubed or pounds per foot cubed, times the depth that you're talking about. So what are the units then of pressure? Everyone's writing and not thinking. What's that? Right, so it's going to be newtons, or so it's going to be force per area, right? Pressure is force per area. When you do weight density times depth, you get pressure, which is force per area. So our weight density is, we often use rho. I used that in the last example. Depth D. So that's depth from the surface of the liquid. From the surface of the liquid. Okay, so the units then are force per area, either newtons per meter squared or pounds per foot squared. Okay, and then to get force then, so then force is pressure times area. So we have something submerged in the liquid. The total force is the pressure times the area. So when will we need to integrate? So to find hydrostatic force, when would we need to integrate and when wouldn't we need to integrate? So if you have some kind of like plate submerged in the liquid, when would you not need to integrate? How could you just use these formulas? What kind of situation would you have? Yeah. What's that? No, the plate is stationary. No matter what we're talking about, the plate is stationary. But what kind of stationary plate would not require integration? We could just use these formulas. Okay, which is right. How do you get the same? What's that? Right, so it's all about the fact that pressure changes with depth, right? So if you have a plate and all the surface of that plate is at the same depth, you wouldn't need to integrate, right? What kind of plate is that? If all the surface of the plate is at the same depth. Horizontal plate, right? So a horizontal plate, everywhere on that plate is experiencing the same pressure, so you could just use these formulas. Now, what kind of, any other kind of plate, if there's any vertical component to the plate at all, then the pressure is going to change with depth. And we need to find a typical amount of force and add them all up, just like we said with integration. So just easy example here. So let's just do a rectangular plate underwater. And it's, say, 8 feet by 3 feet. Vertical plate. So I find the area of a plate first, right? 24 feet squared. Right? And I'm going to take the pressure. I'm going to find the pressure and then times 24 feet squared, right? No, right? You're not going to find the area of this plate because the force is going to change with depth because pressure changes with depth. So, but we need an element for which pressure is constant and force is constant. So, what kind of element are we going to use to get constant pressure? Horizontal strip. We're catching on, right? We're catching on. Horizontal strip on this plate will be the type of element for which we can calculate pressure using rho times d, and then we can calculate force using P times A, and then we'll add up all the strips, okay? So the pressure, delta P on our strip is rho. So this is underwater, is that 62.5 pounds per foot cubed? Times the depth. Okay, frame of reference, right? Frame of reference. With these hydrostatic pressure problems, I recommend a frame of reference always from the surface of the water. So we'll go back to using X because it's our only thing here. Now, you could use different frames of reference, but I recommend for the water ones, use it from the surface. Okay, so what is D? For this strip, it's just going to be X. And then the little bit of force on the strip is going to be our pressure, right? Times the area. The area of the strip is what? 8 delta X. It's just a rectangle, right? 8 times delta X. And then to get the total force, we're going to sum up all of these. It'll be 62.5 X. The pressure times 8 Delta x is the area of our strip. From what to what? Oh, I never told you how deep. I never told you how deep below it was. So this is 2 feet below. So the first strip that's going to have some force on it is at x at 2, and the last one at 5. That's a real easy one. Okay, so there's 2 web work.